Let's take a look at our first warm-up. We've got a man standing on a scale. On a bathroom scale, we know the only forces acting on him is the force of gravity and force normal. The directions are going to ask us to decide, does the scale say more than his weight of 500 newtons, the same as his weight, 500 newtons, or less than his weight of 500 newtons? We know standing on a scale is not a dietary plan, so his force of gravity is not going to change, only the force normal. And the scale measures force normal, so if the scale is measuring more than 500, that means force normal is bigger than force gravity. If it's less than 500, it means it's less than gravity. So we can do some free body diagrams just showing what would that look like. Force of gravity will not change. It's not a diet program. Force normal can. If force normal and force gravity are the same, we've got balanced forces. Scale says 500. If force normal is smaller, then the scale is going to indicate something less. The acceleration would be down, net force down. If force normal is much larger, the net force is up, so acceleration is up. When we're looking at these pictures, velocity does not matter. What matters is the acceleration. The direction of the acceleration follows the direction of the net force. So if the acceleration is up, for each one of those, net force is bigger than force gravity. It's going to show more than 500. If acceleration is down, that means net force is down. That means force normal is smaller than gravity. The scale will say less than 500. If there's no acceleration, forces are balanced. Scale says 500 newtons. Next warm-up. We've got 4 graphs. They're the same in every way as far as the scale. We're looking at force versus acceleration. And it wants us to rank which one has the greatest mass. And yeah, this is not something we've looked at, but we're smart people. We can figure out what we're supposed to do here. What is the relationship that we have between force and acceleration? Because the graphs are force versus acceleration, right? And if we think about slope, slope is rise over run. So that would be force over acceleration. And if we know force is mass times acceleration, force over acceleration would give us mass. So bigger slope, bigger mass. So which one has the biggest slope? I think the biggest slope is probably coming from C. That's the steepest slope that I see. I think now that we kind of see that, C would be first, followed by A, then B, then D, the last one. As the slope increases, so does the mass, because we're looking at slope being mass. So C, A, B, D. All right, it's time to take some notes. So grab something to write on, something to write with. We're going to take some notes on friction. I know we've done the force of friction a little bit, but let's take a look and see what friction is, how to calculate it, what the formula is. Something to write with, something to write on. Pause the video if you need to until you're ready. So if we're going to talk about friction, let's define what friction is, okay? Or at least a formula for friction. So friction, the force, I need writing tool. I need it to be skinnier and black. All right, now let's false start, try again. The force of friction is equal to the coefficient of friction times force normal. Okay, now what does that mean? Well, there's an easy way to remember that. If we look at FUN and say that friction is fun. So you'll never forget what friction is now because I just told you friction is fun, which means friction is equal to the coefficient of friction times the normal force. So let's define these real quick. So this mu, this Greek letter mu, it looks like a U with a tail on it. That is a coefficient of friction, coefficient of friction. All right, and then we know that Fn is force normal. So if it has force normal as a part of its equation, that should tell us that friction is a contact force. Without contact, you got no friction, because without contact, you've got no force normal. So let's write that down. Friction is a contact force and is directly related to the normal force. All right, so we get normal force, but what about that coefficient of friction? The coefficient is a known value. You can think of it as a constant, sort of. It depends on the two surfaces that are rubbing together. So if we took two things that are slick, so two polished surfaces, and we put those together, and we cause one of them to rub across the other, their coefficient of friction would be very small because they're slick. If we took two pieces of wood and wrapped them in sandpaper and try to scrape them past each other, the coefficient of friction would be very high because they're going to have a lot of friction. They're going to kind of oppose that sliding motion, right? Now, if you have two surfaces, you can look it up in a table and it'll tell you what the coefficient of friction is. You can Google it and say, hey, two pieces of wood, what's the coefficient of friction? Now, yes, there could be some variance because how the wood is sanded and the type of wood it is and which way is the grain going, yes. But the idea is the coefficient of friction is usually a known value. And it varies depending on what the two surfaces are, okay? So kind of wrap our minds around it. The coefficient of friction we could get from a table, okay? We could calculate it based on experimental circumstance, but it's based on the two surfaces that are rubbing together is your coefficient of friction. Now we know the normal force is going to be based on mass, because if we're not moving vertically, we know that the normal force is balanced with the force of gravity, right? And the bigger the mass, the bigger the force of gravity, bigger force of gravity, bigger force normal. So we can kind of get all of that. Let's see, I had something pop up in the chat. Let me scroll so I can see it. What about the coefficient of friction on a puck on ice? If we say that the ice was just cleaned by the Zamboni because we've been watching the Dallas Stars and last night was not a good night to watch them because they lost the second game, but most of the time we're going to say that ice is frictionless. Most of the time we're going to say ice is frictionless. Now, is ice always frictionless? After the Zamboni it is, but right before, at the end of the period for hockey, or right before they clean the ice isn't frictionless because it starts to get layers and all this stuff. But for the most part, for most questions, we'll say ice is frictionless. Okay, let's get through the notes just a little bit. I have a couple more things I want to write down. I want to get into the practice problems just a little bit and then talk about what we want to do between now and next class. So let me scroll this up. We've had enough time to see it. So if we were to draw something, we can say, okay, this is my surface, a little line. So this is my table surface. And then if I draw an object, I've got this free body diagram sitting there. We know that downward would be the force of gravity. We know that upwards is the force of normal. Our force applied would be to the right, so my force applied. And then my force of friction would oppose the force applied. So this would be my force of friction. That's pretty straightforward, okay? I haven't blown anybody's mind with that one because we know force of friction from our homework coming into today opposes motion, right? So we can go through this and say, well, the force of friction is equal to mu times force normal. And then the force of friction, in this case, we can say that we have a sum of forces. So our sum of forces in the horizontal, or in the vertical, let's say the sum of forces in the vertical is the force normal minus the force of gravity, okay? That's our vertical forces in this case. And my object, it's not accelerating off the ground. It's not a rocket ship. It's not accelerating into the ground as if it's, or it's not going into the sky like a rocket. It's not going into the ground like quicksand, right? It's just chill on the ground as far as the vertical is concerned. So that means that the force of gravity, I can say that my net force is then zero if it's not accelerating vertically, right? So my force normal minus my force of gravity, those are balanced forces in this case. So if I add my force of gravity over, I could say the force of gravity is equal to the force normal, right? Those are balanced in this case. if I say that, couldn't I then say that my force of friction is equal to mu times the force of gravity, if they're equal? I'm just taking my original equation and I'm bringing it down here based on that. Based on force of gravity and force normal being equal to each other, I could say that the force of friction is mu times the force of gravity. Only when they're equal, only when there's no acceleration in the vertical for this instance. Okay, so we've got that. Now, what if, though, the surface is a wall? So this is my wall. Okay, here's my object sitting against the wall. This is like me taking my calculator and I'm pressing it to the wall. So if you can still see my video image, you can see I'm pressing my calculator to the wall. I'm applying a force towards the wall, right? So if we go to our picture, my force applied goes this way, force applied. Okay, now my force of gravity is still down. We can test that, not with my calculator, we're not. But we could test that. You drop something, gravity's still going down. All right, force of gravity down. Which way is my force normal going? I want you to unmute and use words. Which way is my force normal moving at this point?
To the left.
To the left, absolutely right. And it's going to the left because it's perpendicular to the surface. Okay, perfect. So my force normal is going to the left. What about my force of friction? Which way should I point it?
Upwards.
Upwards.
Why upwards? Not just because it's the one direction I haven't gone yet.
Because it's moving downwards, right?
Right. The only direction my calculator is going to move at this point is going to be downwards, right? And force of friction opposes movement. So my force of friction in this case would be upwards. Now, if it's balanced, if I balance those arrows up and down, that means it's not moving. According to the way I drew it now, the force of gravity is greater than the force of friction, so it would be moving down the wall according to how I just drew it. If I wanted to indicate that it had a no acceleration, I would need to draw it maybe that long, something like that, so that they have the same magnitude and length of the arrows. I'm not going to get a ruler out, but it should be easy to tell. Okay, so for this one, let's see if I've got enough room to write. Yeah, I do. Sweet. All right, so I'm going to scroll that over just a bit so I can see. We know that the force of friction is equal to coefficient times force normal. That's been stated a couple of times, even on the sheet. And we know that the sum of forces in the x direction, normal and applied, in the x direction is equal to force normal minus force applied. That's supposed to be an n. Let me fix that one. That was just too nasty. Okay. In this case, that is, their forces are balanced because it's not moving into the wall, it's not moving off the wall. So their forces are balanced, that's equal. So here, the force normal minus the force applied, if I add the force applied over, I can say that the force applied is equal to the force normal. Fair enough? Okay. And then if I come down, I can say, what about my summation of forces in the y direction? Would be equal to the force of friction minus the force of gravity. If these are not moving, if this is also balanced, a net force is zero, zero acceleration, equilibrium, all of those things are true, we can say that zero is equal to the force of friction minus the force of gravity, and therefore the force of gravity is equal to the force of friction. We okay with this? We created we couldn't do these equations without the free body diagram. We've got to draw that free body diagram so that we can see what it is and then put it together in the equations, right? So this practice is very important. The last bit of notes I'm going to do for friction, I'm going to scroll this up just a bit, and I'm going to write down something that I want to make sure that it's clear, and that is friction always opposes motion. Friction always opposes motion. So what if we had something that was on an incline? All right, that's my little surface with the lines. Okay, and then this is my object. Okay, now the force normal, I'm going to draw these so that we can see it. And it's also hard to say verbally across the Zoom for you to guess what it is. But my force normal is going to go this way right here, right? Because it's perpendicular to the surface. So this is my force normal. Now my force gravity. With your hand, point to me, what is the force gravity going to look like? Absolutely right. Yes. Force of gravity still goes straight down. So we see in this example that force normal and force of gravity are not straight in line with each other. The force normal is perpendicular to the ground, but if the ground's at an angle, gravity doesn't care. Gravity still goes straight down. So if we're pushing this object up the incline, our force applied would be this way, and our force of friction would be down the incline. All right, let's apply what we know. Friction is fun. Friction is fun because the force of friction is equal to coefficient times force normal. We've got a 10 kilogram object that's at rest on a table. That table's probably on Earth, so we've got a force of gravity of 100 newtons. Force normal would also be 100 newtons because it's at rest on a table. It's not launching up or down, not vertically at least. Coefficient of static friction is 0.6. The kinetic friction coefficient is 0.3. Of course, we need to see if we're overcoming static friction first. And static friction, it only does what it has to do in order to maintain a balance. That's how you maintain a lack of moving, is that your forces are balanced. So if you're applying a force of 30 newtons according to 1A, have you overcome static friction? Well, let's calculate static friction. Friction is force of friction is equal to coefficient times force normal. Coefficient being 0.6 for static, normal being 100. That means the force of friction for static is 60 newtons. We have not overcome the force of friction. Since the max value is 60 newtons and we're only pushing with 3, static friction will only respond with a value of 30 newtons to keep things balanced, to keep it from not moving. If it displayed all 60, you would get an acceleration to the left. It'd be dangerous to push something because it would attack your legs, right? So the force applied is less than the force of friction static max. So there is no velocity, there is no acceleration. And this just says static friction will match the force applied. It'll make sure your forces are balanced until it's overcome. With B, if the force applied is 60 newtons, determine the frictional force and acceleration. Again, we have to calculate static friction. Yes, we did it a second ago, but it's good practice. The force of friction is equal to the coefficient times force normal. The coefficient of static being 0.6, so static friction is 60 newtons. Did we overcome it? We're pushing with 60. We did not overcome it, we only met it, we matched it. So the static friction will be 60 newtons. We've hit the max, but we have not overcome it, so we're not put into motion. There is no acceleration. Velocity is still a constant 0. The static friction must be exceeded, and we did not exceed it. We only met it. No velocity, no acceleration. But what if we push with 70 newtons? If we push with 70 newtons, we know we have overcome the static friction. We've calculated it twice now to say that it's 60 newtons. Now that we have overcome static friction, we throw it away. It doesn't exist. We don't care about it. Forget about it. We are only looking at kinetic friction. When we look at kinetic friction is always the value you calculate. Static will match things to keep things balanced, but once you overcome it, kinetic friction will be a constant value as long as you're in motion. Coefficient times force normal. So we're pushing with a force applied of 70 newtons. 10 kilogram object, force of gravity would be 100 newtons. Force normal, 100. We're balanced vertically. And then the kinetic we calculated is 30 newtons. Now we know the net force is equal to mass times acceleration. They want us to calculate acceleration. So acceleration is the net force divided by mass. The net force being force applied minus force of friction, so 70 minus 30, divided by the mass of 10. So that would be 40 over 10, or 4 meters per second square. Number 2, they're giving us a little bit of a puzzle, so we're going to fill it in as best we can. We can see that it has a constant velocity. Constant velocity means the net force is 0, and they've already said at the bottom the acceleration is also 0. So the mass is 10, so the force of gravity is 100 newtons. Force normal is 100 newtons. Now that we have the force normal times the coefficient of friction, it would be 100 times 0.2 is 20 newtons, so friction is 20 newtons, and if there's no acceleration, the force applied would also be 20 newtons. Now we finished that one. All right, great job. Let's take a look at number 3 and 4. If you want, you can pause the video and then check your work, but let's go through the work if you're doing that now. We've got a mass of 5, so the force of gravity would be what? Force of gravity is going to be 50, force normal is going to be 50. We have a rightward acceleration of 2 meters per second. We know the net force is mass times acceleration. If mass is 5, acceleration is 2. 5 times 2 is 10. So let's get the gravity and the normal in. We've got the net force, we've got all that in. If we've got normal times coefficient, that would be 50 times 0.1, which is 5. And we know net force is equal to mass times acceleration. So force applied minus the force of friction is equal to ma. Force applied is what we're looking for, and we're going to subtract 5 for the force of friction is equal to the mass of 5 times the acceleration of 2. So 5 times 2 is 10, and add that 5 to the other side would be 15. So the force applied is 15 newtons. Looking down to number 4, a rightward force of 25 newtons is applied to a 4 kilogram object. So we're going to put that 4 in real quick. 40 newtons for the gravity, 40 newtons for the force normal. Across a rough surface, 2.5 acceleration, gravity, just basically figure out all the stuff. Well, our net force is 10 because we know that's mass times acceleration. And if the force applied is 25, if we subtract the net, we would get what the friction is, 15. Because 25 minus 15 would get us the net of 10. So we can put in the friction as being 15 newtons. And if the force of friction is equal to coefficient times force normal, we would get 15 is equal to coefficient times 40. And divide both sides by 40, and we're going to get what that coefficient is. If I remember correctly, it's like 0.375 or 0.325. Yeah, 0.375. No units. All right, now we're looking at modified Atwood machines. And Atwood machines just basically have a mass sitting on a tabletop with a mass hanging off the side. They'll get more complicated as we go along, but let's just look at what we have, see what we can put together. We're going to summarize the picture by doing free body diagrams. We're always doing free body diagrams for forces, and they also have spaces for us to do our net force equations, so we're going to fill those in. I'm going to go ahead and put the acceleration of 2 meters per second square in the diagram, just showing, hey, it is going to the right and going down. For our object on the tabletop, there's force of gravity and force normal, but we can see that the object would be pulling to the right. So the force of gravity and force normal are going to be balanced because it's not accelerating vertically for the object on the tabletop. For the object hanging off the right edge, we've got gravity pulling it down and tension pulling it up. The tension in this system is internal. The tension pulling up on the object dangling is the same as the tension pulling to the right for the object on the tabletop. Looks like we've got our net force equations all written, and let's do something called a big freaking object where we put everything together. One big mass. So the mass would be 10 plus m, and pulling it, I'm going to simplify it and say pulling it to the right because it goes to the right before it goes down. But the only external force acting on it is going to be the force of gravity. And force of gravity is calculated as mass times the acceleration of gravity. So we can abbreviate force of gravity as mg. It works because the mass of the dangling object is m. So acceleration is net force over mass, correct? So the net force in this case is simply mg. That's the only external force acting on our system. Tension is internal. It's only touching things that are a part of our system. It's internal. It is not an external mass. External force. So when we put this together, acceleration is 2. mg is m times 10. And then the mass is 10 plus m. If we do a little cross multiplication, we get 20 plus 2m is equal to 10m. And we're just simply solving for the mass. Subtract 2 from both sides. You'd get 20 is equal to 8m. Divide 8 from both sides. 2.5 kilograms is my mass. This is weird. It is different. Stick with the problems and let's see what we can learn. Don't give up on it until we're all the way done, and still don't give up. Now when we're calculating tension, that internal tension, we're going to symbolically cut the rope. So we can look at a single object now. We've got tension pulling up on it, and we've got force of gravity pulling down. Now that we know the mass, force of gravity is 25. Tension is pulling up. We know the acceleration of the system, which is the acceleration of each individual object. Net force is equal to mass times acceleration. Net force is gravity minus tension is equal to ma. 25 minus tension is equal to 2.5 times the acceleration of 2. So 25 minus tension is equal to 5. So 20 should be our force tension, 20 newtons. Let's do a couple of more so that way we get the hang of it. This is a learning process. You can't give up on it. Don't just copy it down. Let's put thought into it. The mass on the tabletop is 10 newtons. It's got a force normal up of 100, force gravity down of 100. There's a tension pulling to the right. We can see the rope, the cable, or the cable. They're calling it a cable. And this time there's friction to the left. The mass hanging down has gravity pulling down on it, and gravity is calculated as mg, and it has tension pulling up. Same tension pulling up is the tension pulling to the right on that top mass. The net force in the x would be tension minus friction. Net force in the y is gravity minus normal. On the hanging mass, there's nothing in the x. On the hanging mass, gravity minus tension. Because it's accelerating down, gravity is going to be bigger than tension. Now it says, what is the maximum mass that could be if the hanging mass does not move? So if it's not moving, we're not using kinetic friction, right? We're only using static friction. And we're going to use the maximum static friction because what's the maximum mass before it moves? So force of friction is coefficient times force normal. That's equal to 0.6 times 100, right? Because that would be force normal for that object. So the force of friction is going to be equal to what? 60 newtons? So we've got a force of friction of 60 newtons to the left, and this object is not moving. So the external force to the right has to be balanced to that, correct? So we're looking at a big freaking object, a BFO. We're combining the masses, and we're looking at the entire system. We have 60 pulling to the left. We have mg pulling to the right. If our net force is equal to mass times acceleration, and acceleration is 0, remember it's not moving, that means mass times acceleration is 0. So my net force would be mg minus force of friction is equal to 0, so mg is equal to force of friction, mg being m times 10, and force of friction being 60. So I can add 60 to the other side, say 10m is equal to 60. M is 6. The mass is 6 kilograms. Number 3. We have a 5 kilogram mass sitting on the horizontal table, connected to a pulley. Hanging down is a 10 kilogram mass. Same free body diagrams, normal up, gravity down, tension to the right, friction to the left. On the other one, we're going to have tension up, gravity down. The net force equations will match our free body diagrams. Larger forces subtract smaller ones. If they're the same, it doesn't matter the order. I usually just kind of do gravity minus normal, and then tension is bigger than friction if it's in motion. They gave us a coefficient of static and kinetic for this particular problem. So we need to determine, are we overcoming static? If we're not, the acceleration's zero and we're not moving. So let's first calculate static friction and see if mg is larger than the static friction that's opposing it. If it's not, we're not moving. It must be larger. Big freaking object. Total mass is 5 plus 10, so we have a 15 kilogram big freaking object. Gravity pulling to the right at 100 newtons. Force of friction. Let's calculate that static friction. Static friction is going to be the coefficient of static times force normal. Coefficient of static is 0.5. Force normal, because the mass is 5, force normal then would be 50. So we're going to get 0.5 times 50, and half of 50 is 25. So static friction is going to max out at 25. Did we overcome 25? Well, we're pulling with 100. 100's bigger than 25. Static's gone. Forget about it. We've overcome it. It's in motion. We're only looking at kinetic now. With kinetic friction, force of friction is equal to coefficient times force normal. Coefficient is 0.3. Normal, still 50. So 0.3 times 50, we get 15? Yeah. Force of friction is 15. Now that's the value we're going to use, because that's the value that's actually applied to our system. If we're pulling with 100 newtons, we're in motion, kinetic friction, 15 newtons opposing us. Acceleration is net force divided by total mass. So 100 minus 15, or gravity minus force friction, over the mass of 15. So 85 divided by 15. Put that into a calculator. Let's see what we get. 5.67 meters per second squared. That's our acceleration. Let's put that in the box. Next, it's asking for tension. When we're looking at tension, we're going to symbolically cut the rope and look at one object, because it's internal. So we're going to kind of cut it and just look at the one thing. We're not actually cutting it, just symbolically. And we're going to say, well, net force is mass times acceleration. The net force for this object that's hanging, we've got gravity minus tension is equal to ma. Gravity is 100 minus tension is equal to mass of 10 times the acceleration. If the system acceleration is 5.67, so is that of the hanging object. Let's just do the algebra. Multiply by 10, and then we're going to subtract 56.7 to the other side, add force tension to the other side. Force tension is 43.3 newtons. Number 4, the final problem of the day. We've got 5 kilogram mass resting on a smooth horizontal table, and then we've got a 10 kilogram mass hanging. We're going to do our free body diagrams for each and our net force equations. It does tell us that the tension is 35 newtons, so I'm just going to show that symbolic cut and saying that the tension in my rope is 35 newtons. Normal and gravity. Normal's up, gravity's down for the object sitting on a tabletop. Friction to the left, force tension to the right. For the object hanging, I got force tension up, force gravity down. And let's fill in those net force equations. It looks like I put force applied instead of force tension, so let's fix that real quick. Force tension, let's make it look good. In the x direction, we got force tension minus force of friction. In the vertical, we have force gravity minus force normal. In the x direction, there's nothing. In the y direction, we have force gravity minus force tension. Since they gave us the force of tension, let's go ahead and do that symbolic cutting of the rope and say Fg minus Ft equals ma. Force of gravity is 100. Force of tension is 35. Mass is 10. Solve for A. 100 minus 35, 65, equals 10A. Divide both sides by 10, 6.5 meters per second square. That's the acceleration of this object. It's the acceleration of the other object. It's the acceleration of the system. So 6.5 meters per second square. Now we want to find out what's the coefficient of kinetic friction. Well, I need to know what friction is to calculate the coefficient. So let's look at that top object. That top object has tension to the right at 35, friction to the left at some value, and we know net force is equal to mass times acceleration, so tension minus force of friction is equal to mass times acceleration. We do tension minus friction because it's moving to the right. It's accelerating to the right. So 35 minus friction is equal to mass of 5 times 6.5 acceleration. 35 minus force friction is equal to whatever 5 times 6.5 is, so 32.5. Subtract the 32.5 to the other side, add force of friction to the right. We get 2.5 newtons is our force of friction. Now that we know what friction is, we know what force normal is, we can solve for the coefficient because the formula is force of friction is equal to coefficient times force normal. 2.5 is equal to coefficient times force normal is 50 in this case. 2.5 divided by 50 will get us our coefficient. All right, I know this is a challenging work. It is difficult work, but stick with it. We learned a lot of new material today. Don't get discouraged if you didn't fully understand it. Just take your time with it. Review the video again if you need to. I'll be at school tomorrow to answer questions. Now that we finished this, go back to that homework packet that was passed out at the beginning of class and work on that until the bell. Thank you guys, and I will see you tomorrow.